that I am running in Spain at the National Spanish Council for Research. My intervention is composed of the following parts. A short introduction to current energy scenarios, a part on the activity which I started implementing already when I was in the University of Perugia in Italy with Baker Hughes and their production site on Florence. And from which activities the project is also born and developed. A feasibility study on integrating chemical looping combustor into gas turbine cycles, economic and environmental impacts, and the GTCLC-NEG project and further developments. So as we know from IRENA, these are 2022 statistics, renewable energy is surely growing. There is much investment on it. But on the other hand, from these statistics proposed by Rystad Energy, which is an ONG based in Norway, we see that fossil fuels are, let's say, stable, not decreasing so much as we expected, for example. And for this reason, carbon capture and storage could be a good solution to allow us to transition to new energy sources, but on the other hand, keeping some of the plants that we have, as we will see in the first case study that I will present. The natural gas combined cycle plants in Italy are a big reality. They are responsible for the production of great part of the energy at the moment in Italy. So I think it's difficult to replace this in a very short time. Together with the carbon capture and storage, we introduce also the topic of carbon negative technologies. Bioenergy with carbon capture and storage, in fact, is a carbon negative technology. It is highlighted and promoted also by the IPCC reports. The main advantage of this technology is that it could allow us to use current technologies working with fossil fuels and have and achieve the net carbon emissions targets, which are diffused and have been pledged by many countries. So mainly carbon negative technologies or bioenergy carbon capture and storage, which is a form of carbon negative technology. We have many other different. It is mainly based on the absorption of CO2 from biomass during the photosynthesis process. And when biomass or biofuels in general, after a step of conversion, are converted into energy mainly by combustion in thermochemical power plants, we can store CO2 on the ground, achieving net negative emissions. So this is the main concept of the technology. As I said before, developing this carbon negative combustor, which I will show, we have to start with some activities of which we developed at the University of Perugia in Italy with Baker Hughes. Baker Hughes has a quite big production site in Florence, Italy, where they produce turbines with the capacity of 12 megawatts and 14 megawatts, for example, which we we think they are more suitable for bioenergy or biomass because, as you know, biomass is dispersed in the territory, so we cannot allow to make very big power plants with with biomass, but we have to focus more on decentralized power plants. So mainly with Baker Hughes, we were responsible of tracing all the carbon emissions in the production of the raw materials, which are used for gas turbine production, which are mainly steel, different alloys of steel, and different materials. And we, together with the company, we started analyzing what happens because this is a multinational company. They have a big supply chain. So what happens if the supplier of raw materials like steel is a developing country? And what happens if it is a country with a low carbon footprint of the energy mix, for example, so electricity or heat, which are produced with less emissions. Here in white, we see, let's say, the emissions which are correlated with steel production if it's done in Europe, for example. And the black one could be developing countries like China and India, for example. The company wanted to know more or less which was the carbon footprint for all the raw materials. Then we have developed all the carbon footprint for all the operations which are happening in the plant of Florence. And at the end, we obtained the result with the different carbon footprint of the different, let's say, components of the gas turbine. And this allowed the company to perform certification of the carbon footprint of the production of 2 models of gas turbines. Here we have to explain better some aspects. First of all, as we know, the carbon footprint of a gas turbine is not focused on production. Production is a small portion of the total gas turbine carbon footprint. As we know, the biggest proportion is the burning of the fuel. So it's the new fuel that we have to produce. And as we know, the gas turbine sector is mainly shifting to hydrogen for achieving net carbon emissions. The technology we propose will have to compete on the market with hydrogen, for example, and also oxy-fuel combustion, because there are trends now that say that if hydrogen is green hydrogen is produced massively with electricity, green electricity and electrolyzers, then we will have a huge flow of oxygen as a subproduct of hydrogen production. So mainly this oxygen could be used in oxy-fuel combustion. So we are well aware that the technology we propose should be fight to find a niche in the energy transition market where other technologies are also developing. We are also aware that the decarbonization of the oil and gas industry is passing for sure through the use of LCA. For example, other companies like Siemens Energy are adopting it on a large scale. So we think that this work could lead to good result also in the selection of the most interesting technologies. So coming to the technology we propose, chemical looping combustors. This was the draft of the plant which I proposed in my project when submitted to the European Union. And this is not a new concept, because it was already dealt by University of Vienna. Here we see also a former publication of Dr. Wolf and Dr. Jan, who is chair of this conference, by the way, already in 2005. And also a publication of Milan Polytechnic University. So here, for example, is the scheme which was firstly proposed by Dr. Wolf and Dr. Jan. And we know there is ongoing some research also at the MIT, because this is, given that this conference is at the MIT, I thought it was interesting to show the publication of 2018 in Applied Energy, proposing such a similar technology. Mainly in the case of the MIT, a reactor which is a rotating reactor was proposed. So mainly by the point of view of the chemical looping combustor, it was more compact, and maybe it could reduce the investment costs. So why there is need of another project? So these technologies have anyway some technical barriers that have to be overcome. For sure, we need more efficient oxygen carriers. So as we will see, the oxygen carrier is what transports the oxygens from air to the fuel for the oxidation. And there is much research ongoing on this, also testing molecular dynamics and all the mechanisms possible to optimize its working conditions. Also, the oxygen carriers need to have low attrition. So during the process, which is happening in most of the cases in fluidized bed reactors, we don't want the oxygen carrier to produce dust. Also, because this dust is very probable that we will find this dust in the gas turbine, and this is the barrier number 4, I think. Then, from my point of view, the most important barrier is that if we need a chemical looping combustor to be coupled to a gas turbine, we need to operate the combustor at high temperature, let's say from 10 bars, 12 bars, and high temperature. So 1200 maybe degrees. And here we have issues both with the material of the reactor that we will see after a few slides, but also with the oxygen carrier, because if we use copper, for example, we know that this copper could give agglomeration inside the fluidized bed. Then the major of the problem is electrical efficiency, but we can maybe discuss this in after the presentation, because electrical efficiency is very important for fossil fuels, because we have to spare them. But if we do a carbon negative technology, this means that the more fuel we use, the more CO2 we have absorbed by the atmosphere during photosynthesis. So we can discuss about the importance of the efficiency. Maybe this could be balanced by the importance of the return on investment, let's say so. So coming to chemical looping combustion, this is a combustion which does not use air. It uses a metal oxide, which provides oxygen to oxidize the fuel, and so it produces a pure flow of CO2 and water, which are the products of combustion, without the nitrogen coming from air. And so we can separate CO2 from water by water condensation and have a pure flow of CO2, which can be captured at very low cost. So first of all, we made an analysis before presenting the project based on Italy energy scenarios. I said that Italy is deeply focused on combined cycles. And we have some national energy strategies which propose an increase of renewable energy, but show that these natural gas plants will remain, I think, in the at least future 10, 15 years. So we have made different scenarios using energy plan software developed by Aalborg University. And mainly the energy scenarios were validated on the targets of the Italian energy policy up to 2030. Obviously, this changes quick. Mainly the policy documents are before the Green Deal, so we can see that maybe this will change a little, also depending on geopolitical issues about natural gas supply, but it's very probable that our natural gas supply power plants will still be quite important. These are our 57 natural gas plants, all in Italy. And our first feasibility study wanted to know what happens if these plants are substituted with a combustor, only the combustion part, which is a chemical looping combustor. This is an example of the combustor, is the one developed by National Energy Technology Laboratory. So these are the power capacity of the plants, the combined cycles in Italy. And this is the electricity generation. What we calculated mainly is how much the CO2 emissions can be reduced and how much could it cost, how much would be the investment to upgrade our current energy system. And you see that the total investment, even if we speak obviously about millions of euros, the total investment is not so high if we compare to the existing energy system now. Obviously, this depends on the carbon price. These were estimates 2030 that said we would arrive at 50 euros per ton, but we are already at almost the double. So if we consider the carbon credit value, we could arrive that the business as usual, which is orange, could be very similar as an expense in investment and operating costs compared to the new proposed scenario. This is to say that instead of changing completely the energy mix of Italy, introducing massive introduction of renewable energy, we can upgrade our natural gas plant in a way that they are carbon neutral. If we use biomass or some fuels, mainly biofuels, this technology can be even carbon negative. So to develop this combustor, I went to Spain. Here is Zaragoza. And our center is mainly focused on combustion and gasification. We prepare the oxygen carrier, we test it in plants, and we do scaling and optimization. These are the batch reactor and the continuous reactor that we have. This I already explained the plant. And the project is based on the preparation, characterization of the oxygen carrier, batch test, modeling, and continuous pilot tests. So compared to the literature, which was most focused on Aspen theoretical studies, we do proper modeling and experimental campaign to see if this technology can work at high pressure and high temperature. We can say that chemical looping combustors working at high pressure are very few at the moment. There is only one project at Keynote, Canada, working in such combustor, and another project in Norway. So we want to bring more data by a scientific point of view. This is the models we are developing with the MFIX software developed by National Energy Technology Laboratory at Morgantown, and the NETL is part of the DOE. And this is the modeling platform with the kinetics, which is done in a pressurized condition with the PTGA. And these are some results: the production of gases and how the reactor works, and the oxygen carrier, how it is converted. The most important result maybe is to see more or less how it works the process. This is biomethane coming inside the reactor, and we see how it turns directly into CO2 and water. What we can see is that at the second 3 minutes and more or less 20 seconds, we see that the reaction path changes completely. So what we are now doing is to analyze one cycle of reduction and to know how much it lasts, and to validate fully our kinetics scheme. The simulation was also done with Huazhong University of Science and Technology. This is our last work, which was presented at the International Applied Energy Conference 2021. And we validate the model. It is with the syngas at pressurized condition. So what happens is that during the reactor 8, we have hydrogen and CO, which are contained into the syngas, that get low because they react at different pressures. And also this was analyzed at different temperatures. Here, during time, we see that the fuel doesn't react anymore. So also in this case, we analyzed the cycle of reduction and how much time is needed to have the oxygen carrier exhausted. It is spent. Our final conclusion on the pressurized model of a batch reactor is that as it was already analyzed by pressurized TGA tests, the hydrogen reaction in the syngas is very quick. The CO is mainly mostly influenced by the pressure, and we have for hydrogen a pressure which is 15 bars, where the kinetics seems to slow a bit. In principle, we can say that syngas behave as the sum of the kinetics of carbon monoxide and hydrogen. From this data, we have calculated the solids inventory that are necessary for our fuel reactor, which is a batch reactor, a fluidized bed. And we discovered that what we expected was an opposite trend. We expected an opposite trend because the effect of pressure on the kinetics is mainly slowing the reaction. So if we increase pressure, the kinetics gets slower. This is what was seen by pressurized TGA tests, while in this case, when we consider also the fluidization and the effect of pressure on the fluidization of the bed, we see that there is an effect which improves heat exchange, and the heat exchange has effects also on the reaction itself. So it balances the kinetics, which is slow. This is at least what we saw from these models, and we are going to further analyze this on an experimental scale. This is what the final plant that we want to propose, which is quite similar to the previous one. And we are optimizing it with different software platforms, so not only Aspen, but also CFD modeling. And what we did try to develop is a procedure to develop such combustor. So while these combustors are usually designed based on the primary energy, so the power of the combustor, in this case we have shifted our interest to the gas turbine. So we first choose a gas turbine, then we calculate the air mass flow that should pass into our combustor, and we calculate the fuel mass flow based on a stoichiometric combustion chemistry. We calculated the oxygen carrier circulation rate, and so on. We slowly design all the plant. This is a completely new methodology. And also we have noticed this, that to optimize all the plant, a key parameter is the excess air in the air reactor. If we increase this, for example, from 1.2 the alpha to 3 times excess air, we have two positive effects. One is that the excess air is going to cool the air reactor and provide the optimal temperature. The other is that we can maximize the power production at the turbine and reduce the use of fuel. So this is how we will make it. So our Aspen optimization is mainly based on two equations at the air reactor and at the fuel reactor. Obviously, these are connected, so the heat for the fuel reactor, which has endothermic reactions, will be provided by the air reactor. So these two terms, we can make them equal. And in this way, we have only one variable to optimize, which is the excess air, as I already said. These are shortly the conclusion, mainly natural gas or biomethane has been tested in a model. Syngas also, and the behavior at pressurized condition have been analyzed. With both cases, the kinetic was done already in TGA. I did not present the experiments for clearness, to be clear and short. And we developed a methodology to let's say clear how to design such kind of plants. Surely next future development will be economic analysis, because as I said, we have to compete with the different technologies, which are mainly taking into the spotlight. But we believe that this technology on bioenergy can be used on a small scale. So small scale could be our niche, and we believe we will find our place in a small scale. I acknowledge the European Union for funding this project and the Chalmers University who contributed in Sweden, giving feedback and experience on chemical looping combustion. These are my contacts if further information is needed, and the project repository where you will find the latest results. I finish saying that in the June 2023, there will be the Turbo Expo conference in Boston, so the same city of the conference, and we will try to organize some sessions also here about this technology.
Great.
Thanks.
Well, thank you very much, Dr. Bartocci, for a very interesting presentation. And I have to say that I'm being more focused on the materials world. I was not familiar with chemical looping combustion. This is a very, very interesting technology for the oxygen separation from the air. It's part of the combustion loop. So let me open this for questions. Are there any questions from the group? Right, well, I'd be glad to kick off the questions. So, so being new to this technology, I'm curious. It seems like the entropy of the combustion reaction between the metal oxide and the methane, the entropy change is very different from combustion in air or with oxygen gas. It seems like there's a much larger entropy increase there. So I'm wondering, how does that fundamentally change the efficiency of this, and how is that? How does it relate to other air separation technologies, such as membranes or other oxygen separation technologies from the air?
Thanks for the question. I think that this is a key topic. First of all, to be simple, we can consider that the enthalpy, at least of the reaction, is the same of combustion. So when we join the two, because it is a reduction and oxidation, when we consider that these two coupled, we are speaking more or less about the same enthalpy of combustion. The critical aspect is in some cases the type of the oxygen carrier you can use. You can use copper, iron, nickel, and magnesium. In most of the cases, these are, let's say, some kind of compounds of these metals, let's say so. And if we think copper, for example, copper has exothermic reaction, both at the reduction and at the oxidation state. So this doesn't, let's say, influence the enthalpy of the whole process, but it influences the thermal balance between the two reactors, which is more favorable mostly. And so the oxygen carrier is an important aspect. Another aspect important is entropy. So enthalpy does not change, but entropy changes, and the project is more efficient. If we consider the history of chemical looping, one first plant was made by Ishida in Japan, And the reason why they developed this technology was because they thought that the entropy balance was more efficient, because they separated the reduction and the oxidation, and having, for example, reduction at very low temperature permitted to the plant to have a better exergy, let's say, and entropy balance. So it was not developed at the beginning for carbon capture sake, but it was developed because it was a separate process, like one oxidation and the other reduction, and it was thought that the process was more efficient. By the point of view of the use of a turbine, we have these two problems: the turbine inlet temperature and the turbine inlet pressure. But from the point of view of the turbine, we can consider that in my country, Italy, there was much research on external combustion fired gas turbine, and there were already commercial plants at small scale. So in practice, we can consider this plant as an external fired turbine, because mainly the turbine is driven by the air which passes through the oxidation reactor, let's say so, in pressurized conditions. So the technology could have at least some market niche on the small scale.
Very interesting. Thank you again. Okay. So there's some other questions for the speaker.
Yes, Pietro, thanks for the fascinating talk. In the first part, you talk about the biomass combustion. What are the commercial requirements and who are the suppliers nowadays? And like, what's the largest demonstration plant so far in the world?
Yeah, dealing with biomass, we are testing three types of fuels: gaseous fuels, liquid fuels, and solid fuels. We have to say that solid fuels are the most difficult to test, because during the combustion we have volatiles that are liberated by the solid, but we have also fixed carbon that is circulating in the bed, and it's difficult to burn. So basically, in a chemical looping combustor with solid, we need another reactor which is called carbon stripper, where we deal specifically with the problem of the char, let's say so, which is not fully combusted. And so what we need for the commercial plant is also some pretreatment of the fuel. So we can couple this plant to a biogas plant or to a pyrolysis plant. For example, in many pyrolysis plants, we have the problem of bio-oil or the liquid condensable gases, which can be used in this plant, and we are analyzing this. The only case in which you don't need pretreatment is if you use solid biomass inside the reactor, but this at the moment is not evaluated because we have a pressurized fluidized bed, and I think that introducing also solid fuel could make this further difficult. As far as the commercial plant, I know that there is a project for 600 kilowatt thermal in Calmet Energy. There is and this is the only pressurized reactor. Is rotating, so kind of intuitively similar approach, at least from the one developed also at the MIT. Other non-pressurized reactor, the biggest I know is in in Darmstadt in Germany. And there is also a project between Norway and China, and I think they will do in China soon another quite big plant in collaboration with SINTEF and all the research institute in Norway. So at the moment, this technology can be evaluated as TRL 7, I think, because we are still on the pilot scale.
Thank you.
Great, very interesting. Any more questions? I'd have one more. I wonder if you could talk a little bit about, you talked about retrofitting existing gas turbines. Can you explain a little bit about that more in terms of what parts of the existing gas turbine plant can you keep, and how much new equipment has to go into the plant?
Yeah, these yes, I believe. Let's say so. That's I believe that for doing this in reality, we have to consider also other options like oxy-fuel combustion. Maybe oxy-fuel combustion could be much more easy to retrofit. While to retrofit, I did not, let's say, tell this assumption at first. So retrofitting the technology, if we want to perform chemical looping, we have to be clear that for sure we are going to lose efficiency. How much efficiency we lose? We lose 4 points of efficiency, I think, at least. This could be balanced by, let's say, an economic point of view from carbon credit, whatever, but from an energetic point of view, we are surely going to lose something. And we are going to operate at lower pressure, almost the half, more or less. And it is possible in practice if we scale up this reactor to do such a thing, at least in the future when the technology will be mature. We have I think, to focus research not only on the reactor but on the treatment of the gas, because as we said that the oxygen carrier is going to in part transform into dust due to attrition. We have to find this solution for this problem, which is the biggest problem which hampers a large-scale use. One technique is to use a support. For example, you put the oxygen carrier in alumina or another kind of support, titanium, for example, to reduce part of the friction. And if we work with magnetic materials, an option could be to put a magnetic filter before the turbine to enhance the efficiency of the cyclone, because the cyclone could separate the much as possible, but we have to find some solution to avoid this.
Okay. Well, thank you very much once again. Terrific.